Urbit fanatics. I'm coming at you live from my headquarters with an exciting episode of Zero K, the podcast where we speak with the staggering minds building Urbit, a decentralized operating system for the next 500 years. In this episode, an interview with mopfel-winrux hardware extraordinaire. Mopfel has a deep background in actual hardware, chips, robots, wiring harnesses, gears, the whole lot. You might even call him a real engineer. Today, he talks about the interaction between your Urbit and the metal that it runs on and what that means for the possibilities of Urbit in the future. He also touched on a project that has since been named Lick, which lets your Urbit directly control hardware like peripherals and GPUs. This is very important for the LLM Urbit crossover that's got everyone so excited. You might also get a glimpse or two at the hardware plans of his company, Native Planet, leaving many to ask, when Urbit phone? Here's mopfel-winrux.
So I like to kind of begin with how you came into Urbit in the first place, starting from, if you can remember, the first time you heard that word.
I can.
So give me the...
I'm a Justin Murphy stan.
Okay.
I am.
You heard it here first.
I'm a Justin Murphy stan. His interview with Yarvin.
Justin, if you listen to this.
His interview with Yarvin, put me down the path of reading the white paper. Okay. And just
interesting.
For me.
So that
white paper, I think the white paper is one of the best. I read white papers regularly for my day job.
Wow,
I spec out these systems.
Yeah.
At whatever. So I look at him oh, this guy has thought of they've thought of everything. The question is I didn't understand how Hoon worked when I read it. Oh, you have this. Okay, cool. I can abstract it away.
Yeah.
But it was there. So then I bought a planet. I don't even remember where I bought my planet from.
Okay.
But now my sponsor doesn't exist anymore. I had to switch over to Course Ones.
Yeah.
Anyways, I bought my planet, and then I was fascinated by knock. Okay. I think the idea. So I did embedded design a lot in grad school, and I was in undergrad. I was going to do it in grad school, but
okay.
Anyways,
and embedded design, what is that?
It's chip design and processor design. How do you build it? How do you have this instruction set, which x86, Intel, ARM, all these are instruction sets. How do you instantiate that in a chip logic? Yeah. And I looked at knock and I was like, okay, I could do this in a chip logic. And I went down the rabbit hole of working on the knock PU, which is half finished. But it's how do you instantiate this 12 opcode processor in a meaningful way? And it just took me down the rabbit hole of learning Lisp and all this stuff. And not learning it, familiar with it, but seeing how they did Lisp machines, and it's you can do it. You have to match patterns, and anyways,
that's so interesting. So I promise I wasn't going on too many tangents, but this is too juicy. So just for people who are listening, don't know what knock is, right? Knock is the opcodes, our equivalent of opcodes, right? So
the assembly language of Urbit.
The assembly language is a great way to put it. So so at the end of the day, your software, a normal software, Earth software, has to go down to some instructions that a chip understands, and that's what it does, right? Yeah. Literally an instruction set. Yeah. And that looks a far sight from whatever.
Different.
Yeah, it's
extremely
it would be totally unrecognizable.
It's a book compared to a T-shirt.
And so we were in So we were in Israel visiting the Intel team there.
Okay. Yeah.
And one of my coworkers, we were talking about knock and x86, and so knock has 12 opcodes and fits on a T-shirt. And that has been one of his slogans, was Curtis's slogans. And so my coworker asked these Intel guys, who are great guys, and I have nothing. Intel's one of the most real companies that ever existed.
They do engineering.
Yeah, they really engineer. And he asked those guys, knock fits on a T-shirt. How many T-shirts would x86 fit on that? And he's like, 100, 1,000, a million. He's like, no one can even tell you.
Can't tell you. That's no one's tried.
Yeah. So we're basically talking about, to the instruction set of most Intel chips is going to be basically a phone book's worth of instructions versus 12 that fit on a T-shirt. Yeah. So that's what compelled you.
Well, that's done to optimize, right? That's done for because your Intel wants to go fast. There's physical limitations to building a chip that it can't overpass, so it gets more complex to do ahead of time optimization.
So this is kind of an interesting question.
This is what jets are, what it's worth. Okay. So there's a specific opcode that essentially says pass this data to whatever's running me, and it'll know what to do with it.
Got it.
And I mean, in so many terms, it's a holomorphic to this extended architecture that x86 is.
Got it. Okay, so let me just restate that and make sure I understand. So basically, Intel's trying to make their chips go as fast as possible. Yes. Okay. Rationally.
Duh.
And so they are basically, hack is a strong word, but basically they identify shortcuts that can be taken, and whenever that happens, they add a new operation.
Optimization.
Just not a hack, is an optimization.
Exactly.
To the instruction set. So x86 gets longer when they find out, oh, we can do this optimization. Whereas for us, we essentially just have one code that means optimize this. And we trust that wherever it's running knows how to optimize it best.
We don't trust it.
Okay.
The definitions, I guess we do. The definition states that whatever gets hinted at, we build up on top of this with jets, which we don't have to really go into, but there's the assumption of jets, which you have to match is what you're running in the interpreter it gets the identical results to what is running on your Urbit. So when you replay and I don't have that jet, I should be able to get the same state. Got
it. So if something doesn't have a jet, so a jet is
a jet's a way of saying, hey, there, which is our interpreter. We'll get into that. Compute this in a better way than this knock code that it's equivalent to.
So the fallback is that it would just go very slow, but it would come to the same.
Exactly.
Got it. Okay, so that's an interesting point. So because this is like, actually maybe you can rehearse some of these. Like, why isn't everything knock, right? Like what are the criticisms of knock?
Because you have 12 instructions, right? So you don't have things like decrement or even subtract. The only arithmetic you have is increment.
Okay.
So the way you do a decrement is you start from 0, count up to the value subtracted by 1.
Yeah. Okay.
So I mean, it's big O n time. It's slow, right?
Yeah.
So but the instruction set is complete. Right, like I can build a decrement function using this instructions,
and that's what you're looking for from the opcode.
Yes, that's what you're looking for from the spec, right? And like you can then worry about the engineering details of implementing things later down the line.
Yeah. Okay.
Right, like it's a higher level compute than a chip representation.
Okay, that's interesting. Yeah. So it is kind of like a list, and I think it's interesting to think about that, right? So it's like we're able to be at a higher level of abstraction than the chip representation.
That's what JavaScript is, right? JVM, your JavaScript virtual machine. You compile JavaScript to a bytecode that gets run. Java does the same way, right? Like Java, the old programming language, it gets compiled to bytecode, and then there's a translation layer that's your interpreter.
Okay.
And I guess that's how Urbit gets run on your regular computer.
Yeah. Okay. So actually, that'd be great. We were going to go into this. Yeah. So like, right now. So an Urbit sometimes is referred to as an overlay operating system.
That's fair. Yeah.
Or it is still an application that runs on your computer, right? So what is the relationship between Urbit, you're running Urbit where you're chatting, whatever, and the actual piece of metal that's running it? So how does it kind of get back and forth?
Let's split up. So let's say you have either Mac, Windows, Linux, any operating system. The typical architecture is split up into two different zones.
Okay.
One zone is called kernel space. This speaks directly to the hardware. This says this pin goes up and down.
Yeah.
Right? And in some obscure language, like there's different layers, but that's what the kernel space does. It also manages like memory and all this stuff. This is how you can break your computer by going to the kernel space.
Yeah.
So that layer is usually not touched. Well, if it's touched and messed with, it's not represented in the upper layer, which is the user space.
Okay.
So the Urbit runtime there is a user space application in any OS.
Got it.
So what it initially does is it says, hey, kernel, I need you to give me X amount of memory that I own. No one else can touch it. And then I'm going to build, this is my loom, right? This is what we call your loom. It's started at 2 gigabytes. I think we just heard it was 8 gigabytes soon.
Oh, yeah.
It's exciting.
It's going up. Line go up.
Number go up. Yeah, it's good. Up and to the right.
To the moon.
But it's like, so then inside of this user space app, we're then virtualizing a whole memory arena for our OS.
Got it.
Which is defined by the knock spec along with along with like the shape of an Arvo kernel.
Yeah.
Like it helps with this. Like you can do optimizations because we have this knowledge about this knock machine.
Okay. So let me restate that and make sure I understand. So on my Mac, there is this like the
very
bedrock of it that is the kernel space,
yes.
right? And that deals with the metal.
Your monitor getting things to display, your USB drive, everything.
All that stuff. So so device drivers, stuff like this.
Yeah.
And above that, you have everything else, which is user space, which is actually gigantic.
Yes.
Right.
Yeah. Well, the user space doesn't have limitations to what you can do in it, right? This is how apps work. This is how, like, you have interface to draw on the monitor. You can call those and draw on the monitor, but
okay. Yeah. So Urbit, all of Urbit lives in user space relative to the machine that you're running it on, right?
Yes.
But then within Urbit,
you have the
kernel.
same split.
Yes.
Yes.
All right. So
but because this is a smart way of doing operating system design, right?
Okay.
There are things you don't want not a regular programmer, but a user space kernel dev to be able to do.
Yeah.
Right. Which just makes sense, right? Like I don't want an arbitrary app I install to be able to get all my like security stuff in jail, which is our security vein.
Yeah.
Right. Like there should be limitations to that.
Yeah.
Or there should be a process of it getting it. It shouldn't be blindly able to read it.
Yeah. And then the equivalent, I mean, like on your MacBook, for example, is you wouldn't want a application that you install to somehow, I mean, bugs
turn on your webcam with
turn off your webcam. Yeah. Turn on your webcam is a great example.
Or mess up the webcam protocol, even if it's like not malicious.
Yeah.
Like even if it's like just user error, like mess it up and burn out your webcam, because this stuff can happen. Like electronics are hard.
On Linux, I've done all. So it's sort of like the more kind of like there are things that let you muck around with it more than you probably actually should. Yeah. So if anyone who's tried to install OpenBSD and get a Wi-Fi card working knows this.
Oh
right?
yeah, I've burnt. Yeah.
Yeah. So that's like that arrangement though, right, means that the Urbit is not actually running on the metal of your machine. Or I mean, it is, but it's not. But everything's running on the metal of your machine.
Yeah. Right. Like you're not compiling knock into memory. Just binary. Just like binary numbers that a processor understands. Yeah. No, you're compiling. Well, you are, but you're doing it through this layering, through this virtualization.
Got it.
Which again, this virtualization is done across the board with programming languages. Like Java does this, JavaScript, Python, no, Ruby. I think you can make the argument that it does. Like Python actually has C bindings, which is another way of doing this. But yeah, Urbit is because there's a virtual machine layer there. Python doesn't have virtual machine, so that doesn't work. But because there's this virtual machine layer, that's what that is. That's the there.
So then I guess my question would be, what makes Urbit an operating system then, as opposed to just like an application on your, like, does that make sense? Like I can run the Twitter desktop app on my Mac. Yeah. What is the difference between that structurally and an operating system? And Urbit as an operating system.
So, I think defining an operating system is kind of important here. An operating system is something that
what's the real definition?
Yeah, I don't know what the real definition. I don't know what the real definition is. I'm going to just say how I think of it. Right? Like I don't know the real definition. But if you think about it, an operating system is something that helps you manage a CPU. Like a CPU is pretty dumb, right? A CPU doesn't understand like how memory paging works, or like how, like, running a microprocessor. Like microprocessors are a good example.
There we go.
Oh, I probably shouldn't touch them.
Yeah. This is a rough living dog.
Yeah, right,
here,
man. Like a microprocessor is a good thing. I have direct access to my memory, but then I have like 32 kilobytes means 32 kilobytes.
Yeah.
I can't do anything to kind of like insert swap space. It provides better functionality, a higher level functionality for this dumb chip.
Yeah.
Right. But this dumb chip is this instruction set.
Yeah.
This higher level functionality gets compiled to it. It's the same thing with Urbit, right? You have this dumb instruction set, and this higher level language Hoon gets compiled down to it. And you're building, and it's not really an OS, it's an operating function, but that's a mathematical distinction, right?
Yeah.
Like you're building this user space environment that helps simplify. You don't want to be typing in assembly or knock into hardware.
Yeah.
So that's in managing all this stuff. So that's kind of why, because it's managing this arena of operation.
Yeah.
It's an operating system.
Operating arena.
Yes.
I'm not sure if that buzzword has been
like
used.
This. I'm
I like
going to
that
use
one.
this.
But I mean, so it's interesting because you're sort of like the operating system enables some things.
Yes.
And I mean, I don't even know. Safety is a lot of it, right?
Yeah.
It's sort of like saying, okay, this stuff you actually don't want to do.
Yeah.
It's going to prevent you from breaking, right? So it's almost like this.
Like you have full control. Like you have full control over how this driver wants to expose the things to you.
Yeah.
Which is like, that's good. That's why drivers exist.
Yeah.
Like that's why you have them.
Yeah.
Like,
yeah. Okay. All right.
Yeah.
Interesting.
So if you really want to have fun, try writing a bit bang program on like a Raspberry Pi to bit bang out like serial with like, you have to keep track of a clock. You have to, it's hard. It's like, you don't want to do that.
There's a lot of things going on inside a computer.
Yeah. That's the skill. Like computers have like, our processor speeds compared to when I first started, first looked at computers are insane.
Yeah.
Right. And it's like, oh yeah, could you?
And you need all these conveniences.
Yes, exactly.
So right now in terms of, okay, so that's all, when you run an Urbit on your laptop or on a server, let's just for argument's sake, let's say a laptop, the program that you're running that explain kind of the architecture within Urbit that makes that possible. Does that make sense? Like,
okay.
Like
so
Var,
so Var is the current interpreter we're using. It's really split up into two parts. You can right now I think it's called Lord and Surf. Lord is like what executes all the Earth side commands or Unix side commands. Surf basically executes the knock.
Got it.
It's more complex than that. That's an easy enough visualization for people. The surf part like takes knock, compiles it, deals with like our memory arena, the loom, figures out how to do like allocation, deallocation, all this stuff within compiled knock using bytecode.
Got it.
The part of the Urbit operating system is this idea of vanes, which is essentially the Urbit kernel Arvos equivalent to their modules in the Linux user space, or POSIX even, right? So these are things you can load on top of Arvo that perform specific tasks.
Okay.
So the big ones we have is like AIMS, which is our communication one, Clay, which is our revision control, Bane, which is our timer, right? So if I want to set a timer for X seconds to get notified, like that's a fun, you can build a lot just out of that, right? Like that's huge.
Yeah.
All this, so like all this kind of, all this, there's a bunch of them, but these are kind of the functionality that we expose to user space.
Got it.
Right? So through these veins, we expose this to user space. So what King does then, it translates that IO into user space, into actual hardware, into the physical device itself.
Got it.
So you're doing all these computations. One computation is, hey, send this message to this network. The interpreter goes, okay, I know how to do that.
Yeah.
I'm going to post this to the surf takes it to the Lord. The Lord says, hey, okay, cool. I'm going to execute this to my IO driver. The IO driver does whatever it needs to do. The protocol defined at the high level is, what's the word I'm looking for? I don't know the right word, but it's always going to provide the same result.
Yeah.
Either you get an ACK or a NAC.
Yeah.
Right? It went through or it didn't. It doesn't care about the lower level.
Not referentially transparent.
No, that's not the right term. No. I don't know. That's not the term. It's the fact that you have a state machine that you can replay and guarantee the state. I hate
There's a term for it.
Yeah, there's a term for it. Someone put it in the comments.
Yeah, exactly. I'm sure someone will.
Yeah, I'm sure. I hope so. No, so these so because we can define it at a higher level, we don't have to worry about the Earth side like UDP protocol getting it through. Like we can define a higher level protocol that utilizes this, and that's what the King's in charge of. So like setting a Unix timer to say, hey, resend an event into Arvo when this Unix timer is expired.
Yeah.
It's the same way like your timer works on like a Unix C program, right? You set a timer, you wait, you get a call back.
Yeah. Okay.
It's the same. It's just we ported that into these are basic basic OS functionality.
Yeah. So iOS does it. Anything that runs around.
Yeah, exactly. Like this isn't a common call. I need X timer. Wake me up.
Yeah. So
that's like Bane is a good example because it's so
simple.
It's so simple.
Well, also people don't understand like so many things are just setting a timer and checking later.
Yeah. Like I'm going to wait now. I'm going to go to sleep. I don't need to wake me up, and I know what to do when I wake up.
Yeah. Okay. Yeah. So that's interesting. So as you were saying that, I thought what's interesting is you're essentially restricting. Like, if you imagine this pyramid and you're like sort of like Unix kernel space, Unix user space, Urbit kernel space. It's like it just becomes smaller and smaller. This pyramid, but you're actually restricting what
you're restricting the complexity in Unix provides.
But that's what I was going to ask. Like, what's the benefit of doing that?
You don't have to deal with some Unix headaches. Like because you're building on a Kelvin versioned system, right? You can make the assumption that like your lower level spec isn't going to change. If it does, it's only going to change a certain amount, and you can adapt, you can recompile to it, right? Like your higher level stuff it's not going to break all the time.
Yeah, I mean, this is an interesting thing that I think maybe is worthwhile pointing out because like, I promise not to get too philosophical here, but it's like, in general, you think about restricting things, you're actually, that's bad. But in reality,
it's the opposite.
Right?
It's always opposite. If your assumptions are set in stone firm, then I can make this here like it's an assumption, right? I can prove this out because I have this axiom.
Yeah.
I know, and it comes back to like this knock like how knock works, right? Like I know it's a stateful state tree. Like I know that it's a machine that does this. Like based off all these assumptions that get built up when you strain, you can do things like referential transparency in a namespace, trivially, across a network.
Yeah.
Right? Like across a network, I can go and take someone else's desk and put it into mine and say, hey, this is the app I want.
Yeah. So that's interesting. So if you think about basically, at each level you're restricting your generality.
Thin waist is I think is the technical term. It's
just
like if you have a thin waist, it doesn't matter if your outsides are huge, right?
Yeah.
This thin waist like lets you do things in both directions.
Interesting.
That are freeing.
Your shared assumptions are more secure, basically. Yeah. And so you mentioned something in passing I want to be clear about. So Kelvin versioning is the version system that we use for all of kernel space in Europe. Yeah. Or Europe. Urbit. That's Celsius. Now, that is unique in that it goes backwards. Or
the idea is you want to go down to absolute zero where things are frozen.
Yeah. And so for example, knock, which we've been talking about, which is pretty much the lowest level of Urbit that we refer to as Urbit, is at Kelvin is 4 Kelvin. And that means that we only have three more changes before we've hit 0, and then we basically will not change. So that means that like everything in Urbit in kernel space should be becoming more and more frozen and harder and harder. Yes. And as that happens, I mean, there's an image that is from an old blog post. I don't know if you remember.
I may not.
And it's like a palm tree.
Oh yes.
And so the idea is that the palm tree, is made up of all these things, but the fronds can wave around.
They can do whatever
and
they
so,
want,
the flip side of that security of the core is that then user space can change and whatever, but it can always go back to that secure foundation. So, okay, so I'm sold. I'm into this whole
This is great. I love it.
But what's the downside now? Like, what's the problems with it?
Computers like going very fast in a straight line.
Okay.
That's really what it is. Is like if you look at the knock definition, you have a binary tree, right? Like that's non-trivial.
That's a tree where each
you have two. You have 2 nodes on each tree, right? And a node can comprise of another thing of nodes, or just what we call an atom, right? Well, which we call an atom, which is just an integer number. This could be represented however, but it's just an integer number.
Yeah.
So excuse me. So that's hard to do on hardware.
Got it.
Like that
because hardware
likes straight and close.
Big array.
Yes. Okay, right. It's like that's what caching is. That's what all that is. So the downside is you have to build this interpreter that isn't the fastest to run it. Right. Like
to basically go from this binary tree representation to an array representation.
Okay. Yeah, of some sort. Right. Not necessarily. It's not quite an array. It's a stack heap. It's a stack machine.
Okay. But it's a linear.
It's a linear representation, right? Okay. And there's another effort going on, NuMars, which is looking to do it as a register, which is instead of doing it as a stack machine, doing it as a register machine, which actually makes it faster for hardware.
Okay.
Yeah. So big improvement if it works, like R&D.
Okay.
Yeah.
So actually, this is an apocrypha. I have a question on some apocrypha. Is that sort of like linear representation in memory of a computer? Is that related to the tape that was used in like OG computers, or is there any relationship?
It might be. Okay. Actually, I think it's just because memory is sequential, right? Okay. Like how we've addressed memory since we've had memory as 1, 2, 0, 1, 2. Sorry, I'm not a MATLAB person.
Okay, all right. Okay. Yeah. So that means that basically the way things are now, there's like that transition from the tree structure to the linear structure is just going to be a friction point.
It adds complexity.
Okay.
Yeah.
And that ends up being slowness, basically.
Yeah.
Okay.
Yeah.
And so that's like the main problem with this setup now, you'd say.
I think so.
Okay.
I think because I think hints weren't in Knock 5K, if I remember correctly. I could be wrong about that.
I don't remember.
Yeah, me neither. I think I saw someone's shirt here that said 5K without hints. But like whenever they got added, it just kind of made like in the spec it said there are chips better than me, or there's things better than me that do things that I'm not great at.
Yeah, it may have been that jets existed, but they weren't represented.
Hints,
in Knock.
Or something. Yeah.
Yeah.
So there is that kind. That is a useful command code, right? Just like pass this off to someone else.
Yeah.
As like an instruction set. Yeah. So to bring this to like back to earth, like this is the ARM Intel the debate too, right? The risk restricted instructions. Like, no, Intel made the bet that like we have the manufacturing, we can build a ton of these chips that and just optimize, right? And they won for 40 years.
Yeah.
But power consumption, phones. Yeah. So this reduced, you get benefits from the same kind of thing. You get benefits, but with trade-offs. Right?
Interesting. Yeah. Okay. I didn't think about that. Yeah. And that's sort of like how we've talked about, you know, we always use the V8 example where it's like you have something very messy, but if enough people want it to be fast and you have enough money, like you can figure it out, right? So don't worry right now about making it theoretically fast. That's really not as important. So, I mean, luckily it's worked twice with Intel and V8, so hopefully it works 3 times. Maybe. But who knows? Yeah. So, okay, so the latest thing that you've been working on that we at the Foundation are very excited about is a new vein that is explicitly for dealing with hardware from Urbit. Okay, so why don't you walk us through that?
So we talked a bit about how the OS structure design on Earth, right? How you have kernel space and user space. One of the, so how drivers work in POSIX, right? This is Unix, Linux, BSD, Mac OS, whatever is you register a kernel module or a device driver, and it implements something called an IOTC, IO control, IOCTL, IOCTL. And this is a set of commands that the driver knows, like, hey, this command does X, Y, Z, and I get a memory location in memory, right? Very low level, point me to where I know the status structure, I can deal with it.
Yeah.
This is kernel space, so there are no protections in place, right?
Yeah.
So what this is, it's either like a read or write command for a certain, like if it's a read command, it's put the data in this space. If it's a write command, it's take the data from the space, put it where you want it to put. We need to put it, right?
Yeah.
So that's why you just have a pointer.
Got it.
So that's a system call that any user space Linux app can do to hardware directly.
Got it. Okay.
So if I wanted to talk to like a serial device, which is like USB or RS-232, right? It's a communication protocol. It plugs in USB. I can just, from a C program, I can be like, hey, open the driver. We should get into this. Everything in Linux is a file.
Yeah.
So that means even devices are files. So you can open a file.
Got it.
Right? Okay. You open this file, use this ioctl command to get the settings, read it, modify the settings, rewrite it, and then I'm going to start reading and writing to this file. I'm going to talk to the device there. Okay. So that you can do that in CF, or you can write a library to do that.
Yeah.
Okay.
So, I was just thinking about like, most people's experience with this is like as a printer.
Yes.
No, I mean, the average person is like has dealt with like your printer driver doesn't work.
Yes.
And basically that's just the most concrete example of like you have this piece of hardware, which is a printer, and more specifically the USB interface to the printer, that a program needs to access this piece of metal directly. Yes. Basically. Okay.
Okay. Cool. So that's how Earth works. What Locke is proposing to do is take this ioctl system call command and port that through to Urbit.
Got it.
Or back to Mars, right? However you want to think about it. This protocol I think has been around since the late 60s, 1960s. So it's like one of the few things Earth got right.
Okay.
Is this breakaway. Anyway, so the idea is that we port this to a vein, and the vein can like read or write to it, and it receives a scene or writ command. However you want, I think we're changing the API. I'm sure we'll change the API.
Yeah, so the names will be weird.
always, right? Like it has to be 4-letter.
Is it weirder than ioctl? I don't know,
but ioctl makes sense. IO control.
Yeah, that's true. That's true.
No, I love the naming, but no. So the idea with this is, you would write device drivers in Hoon.
Got it.
And that will do this read and write to either the control plane, the ioctl plane, or to the actual file, or to the actual device itself. And this will be known to do in Hoon and user space. And we restrict this waste again, or we restrict the Kelvin version, so this doesn't change, right?
Mm-hmm. Yeah.
Like even if the Earth side changes, right? We still keep the same thing, so these apps can work through, right? Because Windows does have a version of ioctl. It's not the same, but devices have the same, like
you can print something from a Windows machine. Yeah. Okay.
That's sometimes.
Really interesting. Yeah. Exactly. The gods. Yeah. You propitiate the right dot. So I mean, so just pragmatically, this means you can print stuff from your Urbit, which you actually can't now, right?
No, you can't.
Yeah, that's like so this seems dumb.
So this is the whole proposal is like 3 parts, right? It's getting Lock working, right? Creating the user space helper function. So this is almost like your device driver for Lock.
Yeah.
In Urbit user space, and then creating an actual physical device driver as like a library and marks in Urbit user space.
Okay.
So the first thing we're going to do is we're going to I think we're going to try and get a receipt printer working.
Okay.
So funny, right?
Yeah.
But it'll print out your rumors as they come. So you just have a ticker of your rumors as they come.
Very nice.
Right?
That's
I think
very
it'd be
nice.
a fun. And it'll show all three of those, right? It'll be like this is how the interface works. Like this works. This is how you do threading with it. This is how you do how you get a device with a certain mark. This is how you do the translation of that.
Yeah.
And it kind of will show that to everybody, and then you can let people write their own drivers. It's surprisingly easy to write a lot of drivers.
Okay.
Like a lot of it's just like a one giant memory blob that you modify and rewrite.
Yeah.
But like things like Bluetooth become a little trickier. Different chips have different standards and stuff. And
yeah. But that's really interesting because then it's like, yeah, I mean, but that's also the kind of thing that, I mean, I think about this in terms of how we get contributors to do it. It's a kind of a exercise. It's like, just
this is useful.
Here's a few stars, like go figure out the Bluetooth drivers. That's really interesting. So, and besides that, I'm assuming stuff like a ledger and a Trezor.
Yeah. That's why it's called lock.
Yeah. Aha!
Yeah.
Got it.
Yeah, that's a Neil factoid. Yeah. No, the original idea with this is you can do this can be extended to anything. But like the idea is like, let's say I want to sign something cryptally with my YubiKey, or I want to log in with my YubiKey. I plug it in. I know.
It's a very normie corporate. I'm joking.
I know.
Yeah, it's more hip to reference having a Trezor, but not. But yeah, but that's so just to bring people up to speed on this sort of issue, right? It's like, if you're going to be doing crypto transactions, with your Urbit, your keys have to live someplace, and no matter how secure you make your Urbit, you might not want those keys in your ship all the time. And so if we did this, you could actually have a hardware wallet that connects directly to your Urbit, and that would allow you to have all of basically the exact same security profile as you have now with a MetaMask or something.
Exactly.
Okay.
Exactly. That's
really
cool. And like you can do other things too, right? Like you can if you want to self-update the binary, like what you can do is you can point this to the binary and just rewrite it from my Urbit, right? I can get a blob and just say rewrite to it. Yeah. Like there's another example is like a GPU.
Yeah.
I can take a GPU or a TPU, right? A tensor processing unit, tell it to compute this ML model, give me a result.
Oh, very
like
snazzy.
This opens up a lot of things in Urbit, and it's just people have to go and take advantage of it.
Yeah.
Because
I mean that's always the thing. There's and I suppose with all hardware computing, it's like it probably goes back between generality and specificity, like everything else, right? So it's like a GPU. It's like it is going to be so good. You just want to hook it at a GPU. You don't want to reinvent the wheel.
Yeah,
that's really interesting. Okay, so that's like so anything that's kind of any ASIC, you could probably do this kind of stuff.
What would be fun, like just for fun, is like you can hook it up to like an RS, whatever the small Raspberry Pi is that you can program in Python, and like write a small knock interpreter and offload things to serial and just have an offboard knock interpreter.
Oh,
and just get your data back. Like something silly like that, right? Like just something that's silly like that. Like you'll learn a lot by like looking at a Python knock interpreter and following through with it.
Yeah.
Like so it's just like
Well, and I also wonder if like when this is a different question, but like when you have a bear crypto market, probably a lot of chips lying around that have that are now easily we could use. Yeah. That's really cool. I mean that's wow. I'm even more excited than right? You did it. Fun. You sold me.
I sold you.
Okay, so probably the final question, a little bit of a shift, is like, okay, so everyone who gets into Urbit learns all this stuff at some degree of fidelity, and is like, well, when can we run the Urbit on the Metal?
Okay.
And that's just a question that everyone has asked, right? And we have Native Planet. There's just but that's still that's not purpose built hardware.
Yes.
I mean it's purpose. You know what I mean?
Yeah. Understood.
The processors are not purpose built for Nock, for example. So just can you sketch people out? Like what would that look like? I mean, if you were to just dream with me, just explain to me what would be necessary.
So you would need to instantiate a memory management in hardware.
Okay.
Which is what Veer, which is what the Loom is, which is all this, right? You have to figure out somewhere you have to figure out a module that somehow represents this binary tree in linear memory.
Got it.
Fast and efficient. I should be able to get anything very fast and get it quickly. Seem easily, right?
Okay.
Like even if it's far away, you have to implement that somehow, right? Either you're doing like hardware paging, or you have like another GPU here that does, a CPU here that does very basic forwarding. Like there's different ways of doing it.
Okay.
But that's really what it means, is you have to rethink about there within the kernel space.
Got it. Okay.
Yeah, and that's what I would say running on metal is. Like even if you're writing C code that compiles to bytecode that runs on it, you're running on metal, and that's reasonably. I think that's how you get Urbit on metal. I don't think creating a NOC PU is the right.
Okay, so you don't think making a whole new kind of chip?
I don't think you're going to beat Unix's 60-year head start.
Yeah.
I don't think you're going to beat that 60-year of longer than that iteration and optimization. You're not going to beat that.
Yeah.
Leech off of it.
Yeah.
Use it for what it is, right? There's the complexity of this thing is it's more complex than you, so it should be able to emulate you.
Got it.
Right?
Okay. So you think so you're thinking you'd like try to find some sort of and I mean, are all these register machines equally bad for the purpose? Meaning is like, could you find a kind of chip that is ideal for does that make sense? I don't know how much variation there is in between.
I don't know. Yeah. I don't know.
Yeah. Like, maybe they're not all as bad.
Yeah.
I mean, maybe
or maybe one is just better because it has this, like, what is it? The M2 for Apple like compiles NOC unbelievably fast. Solely
some
because
weird thing.
Well, no, solely because it has a bunch of like cache. Because if you like look at the NOC spec and like draw out the trees of what like the spec means, just on paper, like all it is, it's pattern matching.
Yeah.
So you're going in memory saying, oh, I know this pattern, I'm replacing it with this. That's all a computation is, right? Like you might have to recurse into that.
Yeah.
But like if I have a huge cache, maybe that's the answer. Maybe you have to have chips with giant caches that don't necessarily go fast.
Yeah.
Yeah.
That's interesting. So getting NOC on metal is a hardware problem, or is a software problem rather. It's kind of what you're saying, right? I mean, like
kind of. I mean, I don't think like I've tried to design the NOC PU. I'm like halfway done. I got the hard opcodes done. Like I got recursion with if.
Yeah.
And I forgot the other one done. Like you can find it on my GitHub.
Okay.
If you understand.
Which I'll put in the show notes so you can check that out.
If you understand Verilog, it'd be fun to get some help with that. But if you like I've tried to, and it's just memory reads take a while. Memory writes take a while. That's your bottleneck in hardware.
Yeah.
Like the actual pattern matching isn't that hard.
And that's not even to speak to just the actual supply. I mean, just actual industrial.
Oh yeah. Let's not. We're just talking design, right?
Yeah,
Urbit has to be big enough for this to happen.
Yeah.
There has to be like this is what I call a one-time engineering cost, right? Like this happens X amount. Like you pay for this once and you iterate off of it. Urbit's not big enough to ever see us make our money back.
Yeah. That's a really good point.
Yeah.
Okay. Well, that's really interesting. I hadn't thought about that.
Yeah.
Okay. So just to finish up right now, what are you working on the Native Planet front? What's your role at Native Planet?
I'm the CTO.
The CTO of Native Planet.
Yeah. So right now,
what are you guys doing?
So right now we're doing sovereign self-hosting. Is how do you run Urbit in this odd stack as simple as possible for people?
Okay.
And like we're treating it like a washing machine, right? Like this is an appliance you buy to host your digital life. And that's kind of our design philosophy with it. Like it has to look good, it has to work seamlessly. You don't mess with your washing machine.
Yeah.
Right? Like it has to self-update, it has to have the features you want. And this is the software we're building out, which people can go install and try for free on open source, all of it. So it lets you boot a peer and all this. And then part of this is we built a network proxy that lets you access your peer outside of your home.
Yeah.
You can either host it yourself or we provide it as a service, small fee. But so that's like what Native Planet is. What we're working on now is improved user experience and stuff like automatic backups. Like that's the big thing we're thinking about. Like if I breach, like that's me. Like I'm hosting myself. Like I don't have how do you do this in a secure and encrypted way?
Yeah.
Which we have a path forward. I think we just need to sit down and execute on it, which is good.
Yeah.
We solved the difficult problem. We're also thinking about things like different price points for hardware.
Yeah.
Like not everyone wants to host like 30 people on their peer at the same time, right?
Yeah.
And in additional things like how do we onboard your friends with the Native Planet?
Yeah.
Stuff like this are the questions we're asking. Like how do we make this experience as good as possible?
Yeah.
And then
well, that's great. And the unit looks great, by the way.
Oh my God.
I'll put the URL in the notes and everyone can check it out.
Yeah.
But I mean, the hardware is beautiful.
Yeah.
And I think it's like, what's cool is that once you get people, sort of using your hardware, familiar with it, then inside that box, you can start making all kinds of advancements, right? Because like the user shouldn't even care.
Shouldn't care.
Where it's like,
shouldn't care.
they're like, oh, it's faster. It's like no one they don't know that it took you 2 years of your life to make it.
Why do you as a customer need to worry about this boring stuff?
Yeah, it's like if your customer notices,
it's a problem. We're doing something wrong.
All right, well, thank you very much. This has been super fun.
This has been fun.
Yeah, and I'll put all the information people can look it up.
Appreciate it. Thanks.
Oh,
okay, cool.
How'd that feel?
That's fine. Yeah.